Okay, so let's get back to like power analysis, and now I think you have some background about the AES algorithm, so hopefully what we discuss will make more sense. Okay, so now we discuss about like power traces of AES and so on. So now I think we can understand or try to see a technique which is specifically called as difference of mean, and try to understand how we can use it to crack the key of AES using power observations or power consumptions. So for this, first I will try to talk about a working principle or why this kind of attacks work. So rather this will introduce us to this technique of difference of mean or DOM. Okay. So and like if you observe this and understand this, you will probably gather that this has got nothing to do with the algorithm as such. Okay. Any algorithm can be defeated in this manner because the problem is not really in the algorithm, but is rather lies on the implementation. So if you consider a 4-bit state, say imagine that there is some computation going on, and there is some interesting like register that you want to get. So this could be the key or could be some other secret variable, okay, which is say of dimension 4 bits, and I want to know what is these 4 bits. How do I want to know? Of course, I cannot observe this S. If I know this S, then there is nothing to work for. But rather, I have got some kind of imprint of this in the form of a side channel, which is called as a power consumption of the device. Okay? So I do not directly see that state, but I see a power consumption which is happening because of that state S. Okay? So in VLSI circuits, or in general in circuits basically, I would say one very common way of understanding this power is by describing what is called as a power model. Okay? And a very common power model is what is called as a Hamming weight power model. So Hamming weight power model means that the power consumption depends upon the number of bits that you have 1 in that register. Hamming weight means that if I take an 8-bit number, how many bits are 1 in that 8-bit encoding. Okay? So if it is say, if suppose in a 4-bit number, if I have got say 1010, then its Hamming weight is 2. Okay? If it is 0010, then its Hamming weight is 1. Okay? So the idea is that if the bit is say all ones like 1111, then its power consumption is maximal, but if it is a 0000, then its power consumption is minimal. Okay? So therefore, right, imagine that you are getting the power consumption, and this is where like I think somebody asked me a question that suppose you do not get access to the actual hardware, how you can really still get to do your works. So you can simulate by these power models. Okay? So what you can do is you can apply this Hamming weight power model, and you can simulate what you are probably getting like in your power trace. So in this case, since it is 0000, the Hamming weight stands for 0. Okay? And this is kind of a representative of your power consumption. Right? So what I am trying to do now is imagine that you have got this, I basically write down all these Hamming weights, and now I want to take all these power values, which basically in this case these are numbers from 0 to 4, because the Hamming weight can go from 0 to 4. In a 4-bit number, the Hamming weight can go from 0 to 4. There can be 5 possibilities: 0, 1, 2, 3, and 4. So now what I do is I take all these Hamming weights and I put them into 2 bins. One bin I called as 0 bin, the other one I call as 1 bin. Okay? And I want to kind of basically tell you that I want to make a claim. Okay? The claim is that the power consumption essentially is correlated with the bit of the state. Okay? So what does it mean? It means that if I observe the power consumption, from there I should get some information about the state S. Say I tell you that it depends upon the LSB of the state S. Okay? That is the power consumption depends upon the, or it is correlated to the LSB of the state S. I want to demonstrate that. Okay? So let me try to demonstrate that. Do you understand the claim? The claim is that the Hamming weight of S is dependent upon the LSB of the state S. What is the LSB of the state S? It is these values, right? It is these values. These are the LSBs of the state S. Right? So what I do is, I take this value and I put it into the 0 bin if the LSB is 0. And I put it into the 1 bin if the LSB is 1. Right? Do you understand this experiment? So therefore, write the first value 0, this should go to the 0 bin. The next one 1 should go to the 1 bin. Likewise, this should go to the 0 bin. This should go to the 1 bin and so on. Right? So half of them will go to the 0 bin and half of them will go to the 1 bin. This is understood? Because you have got, the first one is 0, then 1, then 0, then 1 and so on. Right? Right? Is this splitting understood to all of you? Right? So now can you tell me what is the average of the values here and the average of the values here? So you can do this calculation quickly. Can you tell me what is the sum of 0 plus 1 plus 1 plus 2 plus 1 plus 2 plus 2 and plus 3? Can you quickly do this addition? Very simple math. What is the sum? The sum is 12, right? Yes. So therefore one of them will have 12 as sum. This will add up to 12, and therefore the other one will be 20, because the sum is 32. Right? So therefore the average here is 12 by 8 and average here is 20 by 8. So if I take the difference, I will get a non-zero value. I will get 8 by 8, which is 1. Right? The difference of mean is the difference of the delta 0 minus delta 1, and this is in this case 1. Right? So why is this very important? See, I have divided these Hamming weights into these bins based on the LSB of S. Right? If this was randomly partitioned into 2 bins, right, then what would have been the expected sum here and the expected sum here? They would have been same 16 in both cases. And then the difference of mean would have been 0. So if this was randomly partitioned, then the difference of mean would have been 0. But since we are getting a non-zero difference of mean, it says that the Hamming weight is not random, independent of the LSB of S, but it is pretty much correlated with the LSB of S. And likewise, it is correlated with all the bits of S, because there is nothing different between the LSB of S and also maybe some other bit of S. Okay, and likewise it could be even a linear combination of the bits. It will still work. Okay, so this is the very simple funda of the entire thing. That's it. If you understand this, then you get the basics. So this is an example where I try to do this splitting based on some rand function in C, where the difference of mean is pretty close to 0. So I think I have got 15 more minutes. So I'll try to quickly talk about how we can perform this attack in the context of AES. So here are the steps. Okay, so the idea is that you take the you take your AES engine. So it is probably some hardware that you have implemented for AES, or in this case the AES cipher, AES 128 say. So you have a plain text P and you obtain the cipher text C. All of them are of dimensions 128 bits. Okay. So now what I want to do is I want to obtain the key. Okay. So now the idea is that this is a divide and conquer attack, which means I will try to obtain the key in a byte by byte fashion. So remember that the key is also organized in the form of 128 bits, 16 bytes. I'm say interested in this byte. Okay. I call this key as say K0, the 0th byte of the key. And the corresponding plain text is P0. Right? So therefore, right, if you observe the encryption, the first thing that you do is S box applied on P0 XORed with K0. because P0 gets XORed with K0 and then we apply the S box, right? And then you have got an 8-bit value, right? Likewise, there are other 8 bits also, but I'm suppose interested to know what is this particular byte. Okay? So now what I do is I like feed in several plain texts. Like I like feed in maybe like the first plain text P1 and I get the corresponding trace T1. This is the actual power trace. The power trace would look like like this graph that I showed you at the beginning. This is an example of the power trace. Likewise, I feed the second plain text P2, I get T2 and I get the next trace and so on. So I get say like 10,000 or maybe 1,000 encryptions I do and I get T,000 such kind of traces, right? Now what I would like to do is I will I want to know what is this K0 and this K0 can take how many possible values? 2 to the power of 8. So it can take 256 values. So this K0 can take 2 to the power of 8 values, right? So what I do is I start with my first guess. I make a guess, okay, and that guess is say 0. So now what I do is for all these 1,000 encryptions, I calculate S box of like the respective P1 0 0 or maybe P1 0, XOR it with 0 because this is my guess. Okay, I calculate the S box of P1 maybe P2 0, XOR it again with 0 and so on. I do this for all the 1,000 encryptions. Make sense? And now I observe the LSB of these bits. Okay? If the LSB is 0, I take the corresponding trace T1 and dump it into the 0 bin. Okay? If the LSB is 1, I take this T1 trace and put it into the 1 bin. Right? So at the end of the day, based on this guess 0, I will have like the 0 bin containing some traces and the 1 bin containing some traces, right? And I take and I find out the difference of means. I calculate this delta 0 minus delta 1 for this guess 0. This is dependent upon the guess 0. Okay? Now suppose I get this result that this difference of mean is 0 or very close to 0. Then what does it indicate? It indicates that I have done this partition randomly. Okay? And why did it become random? It is because my guess was wrong. Okay? And that's why you get that random behavior where the difference of mean is close to 0. On the contrary, if you had guessed correctly, then you will see that non-zero difference of mean. Okay? And that will only happen for one case because only one is correct and all the others are wrong. Right? So out of all these 256 guesses, only in one case you will see a spike in the difference of mean. Okay? And that way you can distinguish the wrong guesses from the correct guess. Right? And since you can do it for the 0th key byte, you can do it for all the other 15 key bytes. You can do it in a divide and conquer manner. So therefore, even if I make this 128-bit key to 256-bit key, I still cannot stop this attack. Right? So therefore, it is so powerful. The complexity of this attack will be 2 to the power of 8 because you are doing 2 to the power of 8 guesses, but this will be multiplied with 16. In the brute force case, it was 2 to the power of 8, power of 16, and this reduces drastically to 16 into 2 to the power of 8, which is only maybe 2 to the power of 12. Right? No, I tried only for one S box because the 0th key byte I was targeting. This particular key will only get combined with one S box.
Yes, sir. So, sir, total, how many do we need to, like, So how do you do 16 into 2 power 8?
16 because see at this point to recover this 1 key byte I require 2 to the power of 8 guesses, because this guess of the key I did it only for 0, but I have to do was 0, 1, 2 till 255, I mean 255, right? That is 2 to the power of 8 guesses, but that is only for 1 key byte.
So for 16
So you have to do 2 to the power of 8 multiplied by 16, because they are not, they are independent, right? I mean it's not that you are you have to do one for this, right? You can do them in parallel also. Okay, so this is basically the idea. So here is a more description of this, and I think what we will try next, and I think today we are running out of time. This is a more mathematical representation of what just now what I have discussed. I will leave the slides to you. You can look at them. Pictographically, this is what it means. There is an example of DPA being done on DES. This is done on like triple DES. This is done on AES. So you can see for the correct key byte, you get these distinguishable spikes. This is that non-zero difference of means that you are seeing. Okay. For all others, you get a very close difference of means. So it's kind of doesn't stand up. So you can easily distinguish the correct key byte from the wrong key byte. Okay. So I think I will stop here. So this is a summary of the difference of mean based differential power attack. So we are running out of time. So what we will do is, I don't know whether I have a group email. Okay. Okay. Okay, great. So what I will do is, we will basically share a problem statement to you, okay, and you can have a look. It's not an exam, okay, so you can just go back and have it, make an effort, and if you cannot, right, then tomorrow we will start with some actual code execution. Maybe Siddhartha can start with that, okay, and we will show you some actual code execution, because so that you can get a feel of that, and then I will start the portion on fault attacks. Okay. So I will stop here.